In this tutorial, you will learn how to create a physics engine in HTML canvas by recreating this cannon showcase. So as you can see, it does a good job at demonstrating the physics engine because we could shoot balls at different angles and they will be able to be bounced off the walls as well as each other. So as you can see, we'll shoot one now, it bounces off the wall and then it can also collide with the other balls, as you can see now. Now this is known as collision detection, and it is a fundamental part of any worthwhile game engine, let alone a physics engine. So many games would actually be rendered unplayable if there was no collision detection, as the player wouldn't even have a place to stand on for a start. Aside from collision detection though, the other forces working behind the scenes are gravity, friction and elasticity. These are the three traits that are essential to any physics engine worth its salt. So gravity is the most obvious out of the three. It is what makes the balls travel in a slight downward curve. So as you can see, we shoot the ball out here and then it goes in a downward curve because gravity decreases its y velocity. Now, the way that gravity is made is essentially it's a constant value that is being incremented on the y velocity on all objects on every canvas frame, providing that the objects are in the air and not on the ground. Elasticity is what makes the ball's second bounce smaller than the first bounce. So I'm just going to shoot the ball straight up here. And as you can see, the first bounce off the ground and then the second bounce will be smaller, as you can see, and then smaller. So that's elasticity working on the ball essentially. If we did not incorporate elasticity into our engine, then the balls would be able to be bounced up and down forever, never coming to a standstill, as you can see the ball is now. This is obviously far from realistic though, as even objects that are designed to have high elasticity in real life, such as bouncy balls, eventually lose the bounce entirely. Now, both elasticity and gravity are associated with the y velocity of an object, but what about the x velocity? What is there to stop the ball from travelling on the x-axis indefinitely? Well, this is where friction comes into play. Friction does to the x velocity what gravity does to the y velocity. It essentially stops the object from moving in that direction entirely by slowly decreasing the associated velocity. So if we, it's kind of hard to demonstrate this actually because of the canvas boundaries, but essentially, as you can see, it decreases on the x-axis, so eventually it comes to a complete halt on the y-axis, which is the reason why it's not bouncing up in the air anymore. And as you can see, it's also come to a standstill on the x-axis, so it's not moving towards the right anymore. So when these four things are used in tandem, collision detection, gravity, elasticity and friction, we can create a virtual environment that mirrors the physics of our own. Obviously we're oversimplifying things a little bit, as for a start our canvas is only operating on a 2D plane. However, these four key principles are what define a physics engine, and that is why you will be learning how to create them all from scratch by using the HTML Canvas API, and this example here, which will guide your learning by demonstrating how all these different principles coalesce to form a complete package. In an effort not to bore you, I have already set up the markup and styling that I will be using throughout the duration of this video. Here is the markup, and this is the styling. Now on the markup, it is actually worth mentioning the canvas size. Currently the canvas is set to be a square of 600 by 600 pixels. This is important because you may want your canvas to be sized differently, and if you do, then you should be aware that you may need to adjust some of the offset values that are used throughout this tutorial and adapt it to better suit the dimensions of your own canvas. So once you've got that out of the way, it's time to move on to this empty JavaScript file and start writing some code. Since we are working with canvas, we will first need to extract the context from the canvas so that we can actually be able to interact with the canvas on my JavaScript file. Now, as you can see, the finished project has a border around it that is actually rendered inside of the canvas, yet also covers the outer perimeter of the canvas. As you can see, it's this grey rectangle here. Therefore, we will go back to our JavaScript file and we will draw the border to our currently empty canvas here in a new function. So the function starts by using this fill style property on the context to specify that we want all of the below code to use this grey colour that we have assigned to the property. That is of course until we specify another colour. We then use this fillRect method to draw a rectangle onto the canvas that matches its width and height, meaning it covers the canvas in its entirety. Since we want a border and not an overlay, we follow the rectangle's creation with the clearRect method here. This particular one is set to clear the middle of the rectangle that we have just created, so that 20 pixels of margin are left on all sides of the canvas. This is why clearRect starts at 20 pixels offset from both top and bottom of the canvas, and shares the same width and height of 560 pixels. Combine 560 pixels with the 20 pixels offset and a canvas that is both 600 pixels on its width and height, we leave a 20 pixels gap between the border and the bottom right of the canvas. It is reasons like this that make the canvas dimensions an important consideration when you define the offsets for the graphics that you are going to be drawing onto it. Next, we will create this animate function to call our border method so that the border can actually be drawn onto the canvas. However, before we call the draw border function inside this animate function, the first thing in this animate function needs to be the request animation frame method that repeatedly invokes this function on every canvas draw. Hence, all code that represents movement will need to be associated with this animate function, as it is the only thing that will be repeatedly invoked on every canvas frame. It is for this reason that the next line of code will be this clearRect method from the context. It clears out the context of the canvas that have remained from the previous canvas frame. This allows us to draw new things onto the canvas in this new frame without worrying about graphics left behind from the previous canvas frames. Once these two things are done, we can draw our border to the canvas. Its position in the function makes it the first thing that we will render to the canvas on each subsequent frame. Now remember that this request animation frame method does not work unless we actually call this animate method on initial document load. So we will write it out in the JavaScript file here. Now we can go to our project and see the border that we've created. So we have just created the border, and it is now time to create the cannon. Now the cannon is actually split into two sections, the top of the cannon and the stand. The stand is made from a simple line that is drawn onto the canvas, as you can see here. There's nothing difficult about this stand. What is more interesting is this cannon top here, the thing that rotates around. Now the graphics for the cannon top are not actually drawn onto the canvas, per se. They come from a PNG image with a transparent background, and I posted a link in the description to the cannon image that you can use for yourself. As you can see, it's hosted here. The cannon will be created as a class, so we can associate fields and methods with the cannon. So we will start off by assigning its x and y fields to the values passed into the cannon's constructor. We will soon be using these x and y fields to draw the cannon to the canvas. This means that we can initialize the cannon to be in whatever position that we want it to be in. We will then create this method here. Its purpose is to draw the stand part of the cannon to the canvas. Notice that we are not hard-coded in any values here. All of the x and y offsets are based off the x and y fields in the constructor. This is because we want the stand to be relevant to whatever value that we assign the x and y fields, and since we don't know what those values will be, we have to define our offsets in relation to those unknown values. We will then create this draw method. This is the method that will be called in the animate function to get the cannon drawn onto the canvas. But before we can draw the stand onto the canvas, we will need to initialize an instance of the cannon class, so that we can actually have an object to call this draw method from. Now the y offset is set to be 580 pixels. This will make the cannon stand be positioned on top of the bottom canvas border, because obviously we don't want it to be floating in midair. So now we can add this draw method into the animate function that's repeatedly invoked on each canvas frame. And then we can see that the stand has actually been rendered to the canvas. However, the stand is only one part of the cannon. The other part is the top, which rotates around. Since this is created with an image, we first need to load that image into our JavaScript file before we can begin to draw it onto the canvas. Now the problem with images is that they are loaded asynchronously, meaning that there is a chance the canvas loads before the image does, and therefore we will not be able to load our image onto the already loaded canvas. So we will create the image here, and then we will get the link to that image that's hosted on the internet. Again, link to this image will be posted in the description of this video. And then we will assign this image to the src property of the cannon top image that we just created. And to solve the asynchronous problem of the canvas being loaded before the image, so we can't render the image onto the canvas, we will create this function that will be called on the image load. Inside of this function, we will only call the animate function that renders to the canvas unless all of the images have been loaded up first. So we will actually delete this call to the animate function on document load here. What we are doing here isn't actually necessary to our current application because we are only using one image in our entire application as counted by this variable here. Therefore, this animate method will only be called once our only image loads up, meaning that we could just call the animate function straight away without having this if statement here first. However, I'm writing this code in full to show you how you would load up multiple images before you draw them onto the canvas. Therefore, the code I'm writing here will work just as well as they do with 7 images as they do with 1 image. Finally, to get this code to actually work, we will need to assign this render images function to the onload property of the image so that it can be called when the image loads. Remember that if you are working with multiple images, which we are currently not for this project, but this is just a general rule, you will assign all of the images the same onload function, that this if condition will actually work. So now we go back to our cannon class draw method, and then we are going to render the cannon top image on top of the cannon stand. And as you can see, the cannon top has a width of 100 pixels and a height of 50 pixels. However, the problem with this is, if we go back to our application, as you can see, it's hardly even visible on the canvas. It's obviously not positioned correctly. So to fix this poor positioning, we will create these 2 new fields that again derive from the base X and Y fields. And what we are doing here is moving the cannon top back and upwards from the base position of the stand, which come from these X and Y arguments from the constructor. And so now we change the offsets that the cannon top image is using, and if we go back to application, we should see that the cannon top image has actually been loaded to the canvas in the correct position this time because it's on top of the canvas stand. However, obviously there's still some work to do because in the final application, the user was actually able to rotate around this cannon top using the mouse, and obviously we can't do this yet on our current application. So we will start by creating this global variable, and by default it will not hold a value as indicated by null. We only want to assign it a value when the user has moved their mouse on the canvas, and to detect when they have done this, we create this mouse move event listener added to the canvas. Inside we will store the X and Y coordinates of the mouse in relation to the canvas. Now the properties from the event object here are actually in relation to the mouse position inside the entire viewport and so not the canvas. And that's the reason why we subtract these canvas offset values from the viewport to get the X and Y coordinates in relation to the canvas and not the viewport, which is what we want. Now, these X and Y values from the event object are actually in relation to the viewport and so not the canvas, which is the reason why we subtract these canvas offset values to the X and Y offsets of the event object to get X and Y values that are in relation to the canvas. We will also create this angle global variable, and it will only be assigned a value when mouse position has been assigned a value. Then we will create this new method on the cannon class. Its purpose is to rotate the cannon top in relation to where the user's cursor is on the canvas. So if mouse pos is assigned a value, then the angle variable will be assigned the value calculated from this a_tan_2 function. Now the a_tan_2 function works out the angle difference between the 0 degree line, so a flat horizontal line pointing to the right, and the coordinate passed into the function. So if the coordinate that we passed into the function was located here, the a_tan_2 function would measure the difference between the would-be 0 degree position and the new coordinate. This a_tan_2 function does not actually work with degrees, instead it works with radians. All you need to know about radians is that computers find them easier to work with than degrees, and that there are roughly 6 of them in a perfect circle. As for the subtracting, essentially we are getting the difference between the top of the canvas stand and the current position of our cursor. This will give us an angle that's relevant to the cannon. We then rotate the entire canvas by that angle that we have just created with the a_tan_2 function using the rotate method from the canvas context. However, the problem with this is that the cannon won't actually be rotated properly it will be rotated by the angle created between the top of the cannon stand and the mouse position. However, the point of rotation will be related to the top left corner of the canvas and not the top of the cannon stand, which is what we want. This means that the cannon will become detached from the canvas stand when we rotate it with our current method. The solution is to move the top left corner of the canvas to the top of the canvas stand before the rotation, and then move it back to its original position here, after the rotation has been completed. This will alter the rotation origin of the cannon to be the top of the canvas stand, allowing the cannon top to rotate properly in relation to it. We will call this rotate top method inside of the draw method, which is repeatedly invoked inside the animate function. And we will place it before the image is rendered to the canvas, so that the canvas top can be rotated properly before it is drawn to the canvas. Notice that we have also called the save method on the canvas context. What we are doing here is saving the state of the context before the rotation has taken place. This allows us to easily store this unrotated canvas state before other elements are drawn to the canvas. As we do not want them to be rotated, we only want this canvas top to be rotated. That is why we will call this restore method from the canvas context after we are finished with the cannon's draw method. We are essentially restoring the canvas to its unrotated state, so that everything rendered below this ctx.restore line will not be rotated. So now if you go to application, we should be able to see, as you can see, it's actually being rotated, and the border or the stand, that's not being rotated because the canvas is being restored to its default state after this cannon top is rotated, and this is the exact functionality that we want. So now that we have the cannon, it's now time to get the balls being shot out of the cannon, and we send a cannonball flying out of the cannon when the user clicks on the canvas. To detect when this happens, we will create this click event listener onto the canvas. Now we don't want the user to be able to shoot cannonballs directly behind the cannon or directly below the cannon. This is because there is simply not enough room to create a cannonball there. So for example, if they shoot here, obviously we can't really create a cannonball in these places, because otherwise the cannonball would be inside of the canvas border, and that's not what we want. As for the cannonballs themselves, we want to be able to draw more than one of them to the canvas. That is why we will create this empty array. It will hold the instantiations of the yet to be created cannonball class, so that we can loop through the array and render all the different cannonballs to the canvas. So we will create this cannonball class like so. Its constructor takes in 3 arguments: the angle, which defines the direction that the ball will be going in, and the x and y values, which define the ball's starting point. Now as for the fields, as you can see, this radius field is actually hard coded because we want all of the balls to be of equal dimension, and we do include this mass field, and its use will come in later when we get to bouncing the balls off of each other. It shares the same value as the radius because it would only be logical that larger balls made of the same material have greater mass. Now these dx and dy fields define the ball's velocity for the respective axis. The sine method is used for the y velocity because sine corresponds to the opposite of the hypotenuse, or the longest angle, which in our case is the y direction. The cosine means adjacent to the hypotenuse, which in our case is the x direction. Now we multiply both of these values by 7 to add some force to the velocities, so the balls actually feel like they're being shot out of the cannon. We will then create this move method inside of the cannonball class to apply the velocity values to the associated x and y position of the cannonball. This will get the ball moving in a straight line in the direction specified by the angle field. We then create this draw method. This will be the method that gets the cannonball actually drawn onto the canvas. Now going back to our click event listener, we will push a new instantiation of the cannonball to the cannonball's array every time this event listener is triggered. As you can see, it takes in the current angle between the top of the canvas stand and the user's mouse position when they clicked on the canvas, and it's able to be accessed because it's a global scope variable. As for its starting position, we have modified the top x and top y fields of the cannon to make the balls actually come out of the cannon nozzle, regardless of where the cannon itself is positioned. Now, to actually get the cannonballs rendered to the canvas, we will need to loop through the cannonballs array after we have restored the unrotated context in the animate function here. We will start by, inside of the loop, we will first call the move method to get each ball moving, and then we will call the draw method on each ball that is being looped through to render the new ball's position onto the canvas on each of the cannonball objects contained inside of the array. So inside of this loop, we will first call the move method on each ball that is being looped through, and this will assign the new X and Y positions to the ball to get it moving in its specified angle, and then we will call its draw method so that it can actually be rendered to the canvas. So now if you go back to application and we start instantiating balls, as you can see, they are flying around the place and we can't create them in this sort of direction here. However, the problem, as you can see, is that they're only actually coming out of the cannon's nozzle when we are shooting in the right direction. As you can see, they don't even look like they're coming out of the cannon, and this is a major problem. To fix this, we will create a function that takes in the X and Y values that we are currently using to instantiate the cannonball with, and then it should output new starting values based on the current rotation of the cannon top. So once we have stored that current angle inside a new variable, we will work out the difference between the top of the canvas stand, which we set to be the rotation origin, and the nozzle that we want the cannonballs to come out of. And as you can see, you first work out the difference on the x-axis, and then below that we work out the difference on the y-axis. And then finally we use Pythagoras' theorem to work out the actual difference between the 2 points if we just drew a straight line between them, as represented by the hypotenuse. We also work out the angle of this unrotated distance. This will be added to the new angle, allowing us to instantiate the balls in the correct overall angle. So to work out the new starting coordinate of the cannonballs, we first add the distance length back to the top of the canvas stand, so that we can create the cannonballs at the correct length away from the rotation origin. Then we multiply this value by either sine or cosine of the original non-rotated angle plus the new rotated angle. This will give us the correct rotation, which used in tandem with the correct distance means that we have worked out the correct starting position for the cannonballs in relation to the current rotation of the cannon top. And as you can see, we return these new X and Y values in the object that is returned by this function. So back in our event listener, we will modify our code so that the cannonball takes in the result of the sort ball pos function as its starting X and Y positions. And so now if we go back to our application, refresh just in case, as you can see we can shoot the balls, and no matter which direction we've rotated the cannon in, it's now being instantiated out of the nozzle, so not to the side of the cannon, and obviously this is the behaviour that it wants. The problem is the user can spam the cannonballs, which isn't very realistic. Chances are you're not going to see a cannon shooting out cannonballs that quickly. To solve this problem, we will create a boolean, and its value will determine whether or not we can shoot off a new cannonball. So if it is false, then we will not proceed with the rest of the code in the event listener. If it is set to true, however, then we will proceed with the code, and then we will set the boolean to equal false immediately after, so that we will not be able to recall the code in the event listener without something else changing this boolean's value back to true. That is why we will finish off the event listener with this set timeout function. After 1 second, which is written here as 1000 milliseconds, the boolean will be sent back to true, allowing us to shoot off another ball, but only after this 1 second has passed. Another thing that we might want to add would be sound. So when we shoot off a new cannonball, we want a sound to be played when we do that. And obviously the audio that I'll be using comes from this link here. I'll post a link to it in the description. We will set the audio to start playing at 0.2 of a second into the sound file. This is to cut out the slight pause in the sound file before the audio actually starts playing. And so now we can test this out, and actually it's not working. You know why? Because this boolean here, it was meant to be true, but I set it to be false for some reason. So now, if we try it out, as you can see, there's actually audio being played when we shoot the cannons out of the cannon, which is good. Now, obviously, we've got a huge problem here with the balls, and they continue to travel in the same direction, and even surpassing the canvas boundaries, so they just completely go outside our canvas. Now, this is obviously not what we want. We created this border here for a reason, and that's to provide a surface for the balls to bounce off of, so they don't just continue going outside of the canvas. Solution is we are going to create this function, and it will take in the current ball that's currently being looped through, and what we will do is we will see if this ball is colliding with any of the canvas boundaries. So this if statement here will detect to see if the ball is colliding with any of the canvas boundaries on any side, and this first condition refers to the right of the ball colliding with the right of the canvas, hence the reason why we add the radius to the ball's x offset. The next condition detects a left side collision with the left side of the canvas, the third looks for a bottom collision, and the last checks for a top collision with the top canvas border. So inside of this parent if statement, we will create another if else block, and basically what we're doing is we're getting more specific. We will look to see which side of the canvas border did the collision between the ball and the border take place on, and I'll scroll to the side just so you can see the rest of the comment there if you want to. Now, one limitation of the canvas is that it is limited to rendering out 60 frames per second, and that is assuming that there's enough computer resources. That means there is a chance that the ball may already be slightly inside of the canvas border when the collision detection method is activated on the next canvas frame, and because of this we need to set the ball's X position so that it is always touching the edge of the border that it collided with before the rest of the code is called to deflect the ball in the opposite direction, and we will write the code to deflect the ball in the relevant direction now. Notice that if a collision took place on the side of the canvas border, so these two if blocks here, then we will change the x velocity of the ball. Likewise, if the collision took place on either the top or bottom of the canvas border, then we change the ball's y velocity to be minus whatever value it was before. Keeping in mind, of course, that a minus times by minus is positive and so forth. Now that we've created this method, we need to incorporate it into the loop that is invoked on each sequential canvas frame. So now if we go to application, refresh just in case, and we shoot a ball, we should see actually, yeah, it does bounce off the canvas boundaries, and obviously it doesn't do it in a very realistic way. For a start, no gravity is being applied to the ball, so it just goes on forever. The velocity never actually stops, so we need to sort this out. Now, we create this gravity field on the cannonball class, because if we were to create a real application, then we would want to give different objects different gravitational values to simulate the weight of different objects. Now obviously in real life gravity is not relevant to a specific object, rather the environment that the objects are in. However, this is not real life, this is a simulated environment of course. So essentially the gravity will work by continually incrementing the y velocity by this gravity value on every call to the move method, and this will happen so long as the ball is not already resting on the canvas bottom, hence the reason for the if condition, because we do not want the ball to be pushed into the bottom edge of the canvas border as it's already resting on the bottom of the canvas. So now we can test this out, and actually yeah, it's starting to look more realistic now. Obviously we've got a problem here, but the balls are actually going at an arc direction, so if we refresh, just get rid of those, we shoot one out here, and as you can see it is actually starting to go down. Obviously it's not perfect, you know, it's going forever, it doesn't really rest on the floor anymore. However, you can tell that there is some gravitational force being added to the balls, which is good. Now as you can see from the example, the balls were continually bouncing, and the bouncing never actually affected velocity loss. Now the solution to this is to incorporate elasticity into the cannonball, and its value works a little differently to the value of the gravity field, in the sense that it will not be added to the velocity like the gravity was. It will actually multiply the existing velocity value. So because its value is 0.5 at the moment, we will get back 50% or half of what the velocity was previously. In other words, the ball will retain 50% of its previous y velocity on each collision that it makes. And we write this code in the parent if statement in the ball hit war function, because we want the elasticity to be applied to the velocity, regardless of which side the canvas border the ball collided with. And now if we try this out, we should be able to see it actually, yeah, as you can see, it's come to a rest here. Obviously, the problem is it's still moving on the x-axis back and forth, because although it no longer has y velocity to allow it to continually bounce, it does still have velocity on its x-axis. And the way that we solve this is by incorporating friction. And as you can see, it's a very small number, and this gives us the best effect. So on each quarter move method, we will subtract 0.8% of the value of the x velocity from the current x velocity value. This means that eventually the ball will come to a complete standstill on the x velocity, and so this should be good now. So we shoot a ball out, as you can see gravity is being applied to it, and it comes to a rest there. And as you can see, it should, yeah, it's come to a complete standstill. It does seem to be, no, it's completely stopped now. So yeah, I mean, it's not moving anywhere. Its velocity on both x and y is completely zero, and things are looking pretty realistic if you ask me. I mean, obviously you can tweak the specifics, but I mean, essentially, this is what we want. As you can see, it's bouncing, it's smaller bounce now, and then it's come to a complete stop. And this is looking good. And to liven things up a little, we are going to play a sound effect when our boards collide with the canvas edge. Again, the link to this sound will be posted in the description. Now, as you can see, the sound is incorporated a bit differently from what we have previously done. Instead, this sound will be added to the cannonball class itself, and this allows us to have multiple collision sounds being played at the same time from different cannonballs. We will also lower the volume of this sound file so that our application has a consistent volume. We'll actually add some more fields to the cannonball class, all of which relate to the audio file. They are there to prevent us from repeatedly playing the collision sound when the cannonball has come to a rest at the bottom of the canvas and are no longer moving. Technically, when this happens, collisions are still being made between the ball and the bottom of the canvas, yet it wouldn't make sense for a sound to be played on such occasion. And so this timeDiff1 field will only be instantiated with a date value when the ball collides with the canvas border, because as you can see, it's written at the bottom of this parent if statement inside this ball hit war function. And then inside of this parent if statement, we will say if a second collision has occurred and timeDiff1 now holds a value, then timeDiff2 will be assigned the difference between the current time and the time held in the timeDiff1 field. And if the difference is less than 200 milliseconds, then the should audio boolean will be set to false, meaning that the collision audio can no longer be played because the board is colliding too frequently for the board to have even moved since the last collision. As you can see, we shoot out a ball, you can hear the sound, hear the sound, hear the sound, hear the sound, and then it's gone. No more sound, even though technically there is a collision occurring between the ball and the bottom of the canvas here. It's just not playing because the ball hasn't moved, and so it wouldn't really make sense for there to be a sound repeatedly being played when the ball is just stationary at the bottom. So we have done a lot of work and our application looks pretty good. The final thing to do would be to get our balls bouncing off of each other instead of them just acting like the other balls are non-existent. And the first step in getting the balls to bounce off of each other would be to detect when a ball is colliding with another ball so that we can trigger a response when the scenario arises. This function here checks for a collision between two balls at a time. It uses Pythagoras' theorem to calculate the hypotenuse between the coordinates of the two balls, which is also their center point. Then it checks to see the hypotenuse, which tells us the difference between the two balls' center point, is less than both of the balls' radius combined. And if that is the case, then that obviously means the two balls are not separated by the outer circumference, which means that there's a collision. Notice that we don't actually use the square root when we calculate the distance, like you normally would when you use the Pythagoras theorem. This is because the square root is resource intensive, and we can actually get away with not using it in this case because we actually square the sum of both balls' radiuses as an alternate method of using the square root of the distance, and it does the same thing. Since this ball hit ball function only checks two balls at a time, we need to create a loop within a loop, which will allow us to check whether the ball that is currently being looped through is colliding with any of the other balls in the array. So this function takes an index of the board that is currently being looped through and the repeatedly invoked animate function. It uses this index value to create its own nested loop here. Now the loop will start at one board ahead of the board contained in the current index of the array. This is because we've already tested the previous boards in the array for collisions, and we also don't want to test the board against itself for a collision. That would just mess things up. Now since this board hit board function that we just created here, as you can see, it returns a boolean. We know when a collision is occurring based on whether the value returned from the function is true or not. And since this collide function requires the index of the board that is currently being looped through, we will add the second argument to the for each function to get that index value that we need to pass into the function. Then we will call this collide function with the current index as its argument. This is done after the border collision detection, but before the cannonballs are actually fully drawn to the canvas. And this new function will be triggered when this boolean is set to true, indicating that a collision has taken place. And these two arguments will be passed into it. As you can see, we start off by using Pythagoras' theorem to calculate the hypotenuse, or distance between the centre of the two boards that have collided. Now this distance value here is what is known as a vector. A vector is something that has both direction and magnitude, and since direction is angled on the line that connects both the board centres, it has angle, and because it starts at bore 1 and ends at bore 2, it also has magnitude. Now the reason why I bring this up is because we want to transform this distance vector into what's known as a normalized vector. That means removing the magnitude from the vector and getting a value that just represents angle and not length, which is what this v collision norm value is here. We then want to calculate the relative velocity of bore 2 from the perspective of bore 1. Now to properly understand this, imagine that we are in car 1 and are travelling at a velocity of 50 miles per hour. Car 2 is travelling in the same direction as you, but at 40 miles per hour. Therefore, the relative velocity of car 2 in relation to car 1 would be minus 10 miles per hour. And this relative velocity here is very important because on collision, the boards will need to be sent in opposite direction to each other. And the relative velocity is what allows us to do this. We then calculate the dot product of the collision. This is the distance that the relative velocity, which is obviously here, how much it travels on the normalized vector that represents the angle of the collision without the magnitude. And so this speed value gives us not only the correct velocity that the board should be travelling in after the collision, but also the correct direction that they should be travelling in as well. Now, if the dot product ends up being 0, then that means we need to exit out of the function and not proceed with the rest of the code. This is because the boards are already moving out of each other's way, and so we don't need to do anything. Now remember a long while back when we added the mass field to the cannonball class, we were actually going to do something with this value. Mass refers to the measure at which an object resists a change to its velocity, so it is important that we factor this into account when we have objects colliding off of each other, because objects of heavier masses will have its velocity change a lot more. And just because our cannonballs share the same mass as each other does not mean that our physics engine should completely ignore this fact. Finally, we will update the board's new x and y velocities. Notice how we decrement the bore 1 values, but increment the bore 2 values. This is because, as said before, we want the boards to be going in opposite directions from each other. Finally, let's not forget about the elasticity, which needs to be taken care of because a collision has just occurred. And so now we should have done everything and we should have a completed application. Hopefully, fingers crossed. So we shoot out a ball, we shoot out another ball, and okay, we'll shoot out another one. Just so, and yeah, you can see the boards colliding off of each other. And obviously, the more boards that we have, things will start to go wrong because that's just a limitation of canvas. Because there's only so many different boards that it can loop through to detect for a collision within a set frame, and there's only so many computing power to actually do that. So yeah, things will start to go wrong with the board collision detection when you have so many of the boards. For example, they'll start to sort of intermesh with each other, but this code is optimized to the best of my ability, and trust me, it's quite good code and it's also a good physics engine. And so yeah, that's it. We have our completed physics simulation. I hope that you enjoyed this video and learned something useful from it. And if you have any questions, then please don't hesitate to post them down in the comments box below. I would love to hear back from you, and I will answer any question that you may have. And that's all for this one. Peace out.